We're leaving Earth to hunt for life on 3 moons that might actually have it. First, Europa, with a global ocean hidden beneath kilometers of ice. Second, Enceladus, a tiny world spraying geysers loaded with intriguing chemistry. And third, Titan, thick orange skies, seas of liquid methane. Here's the twist. If life exists there, it might not use water at all. Keep watching. Titan could rewrite what habitable means. Stay to the end for our honorable mentions and the missions about to test these worlds for real. This isn't science fiction, it's the short list for life in our solar system. Let's dive in. Europa was discovered in 1610 by Galileo Galilei, but for centuries it was just a point of light orbiting Jupiter. That changed in the late 1970s, when the Voyager probes swept past and revealed something extraordinary. A moon completely encased in ice. In the 1990s, NASA's Galileo spacecraft flew past dozens of times, sending back images of a world crisscrossed with dark lines and fractures, as if its entire surface had been shattered and frozen again. Beneath that ice, scientists believe there's a global ocean containing more than twice the amount of water found in all of Earth's seas combined. On Earth, wherever we find liquid water, from deep-sea hydrothermal vents to icy Antarctic lakes, we find life thriving in forms we never expected. The same chemistry that supports those ecosystems could exist on Europa. Salt detected in its ice suggests the ocean might be rich in minerals, just like Earth's oceans, providing the building blocks life needs. And tidal forces from Jupiter's immense gravity may keep the water warm and circulating, just as Earth's oceans are stirred by our moon and the sun. Strangest of all are Europa's rust-colored streaks, which might be chemicals carried up from the ocean below. Hubble observations hint at plumes of water vapor erupting through the ice, meaning we could one day sample the ocean without drilling through miles of ice. If these plumes are confirmed, they're like nature's own delivery system, shooting possible signs of life into space for us to catch. Soon, we'll get our best chance yet to find out. NASA's Europa Clipper, launching in 2024 and arriving around 2030, will fly past the moon more than 40 times, scanning its surface with ice-penetrating radar and sniffing for chemical traces in the thin atmosphere. ESA's JUICE mission, already on its way, will add even more detail. Together, they'll answer the most exciting question in planetary science. Could a world covered in ice be teeming with life beneath its frozen skin? 400 years ago, Galileo saw a tiny dot of light. Today, we see a world that might be the best place in the solar system to prove we're not alone. Enceladus was discovered in 1789 by William Herschel, but it stayed a distant speck until the Voyager flybys in the early 1980s revealed an unusually bright, icy world. The real shock came with NASA's Cassini mission, 2005 to 2017. Close passes showed a south polar terrain carved by long, warm fractures, nicknamed tiger stripes, and jets of vapor and ice crystals erupting into space. Where Europa looked shattered and refrozen across a vast surface, Enceladus looked smaller, sharper, and startlingly active. Like Europa, Enceladus hides a global saltwater ocean beneath ice. On Earth, life flourishes wherever liquid water, chemistry, and energy meet, especially around deep-sea hydrothermal vents that run without sunlight. Cassini found strong hints of the same recipe here: salt-rich ice grains, complex organics, silica particles linked to hot water rock reactions, and even molecular hydrogen, H2, in the plumes. Europa may hold more water overall, but Enceladus offers something uniquely convenient. It sprays ocean material into space ready to be sampled. What powers those jets, and how stable is the heat driving them? Tidal flexing from Saturn seems to pump energy into the South Pole, warming the tiger stripes and opening cracks that breathe with the orbit. The next leap is to read the ocean story directly. NASA's proposed Enceladus Orbilander would first orbit to map the plumes and then land to analyze fresh fallout, searching for complex organics, isotopic patterns, and other biosignatures. Concepts like ELF and THEO target repeated plume fly-throughs for high-fidelity sampling. Together with Europa Clipper's close passes at Jupiter, we'll be able to compare two very different ocean worlds, one vast and sealed, one small and venting, and ask which is more likely to host life. Titan was discovered in 1655 by Christian Huygens. But even Voyager's flybys in 1980 to 81 saw little more than a smog-wrapped world. The real reveal came with NASA ESA's Cassini-Huygens mission. Cassini's radar peeled back the haze to map rivers, dunes, and vast polar seas, and in 2005, the Huygens probe parachuted down and touched the surface, photographing rounded pebbles of water ice and a landscape shaped by liquid. Just not the kind we know. On Earth, life organizes itself around a water cycle: clouds, rain, rivers, oceans, and chemistry powered by sunlight and rock-water reactions. Titan mirrors that logic with a twist, a methane cycle. It has a thick nitrogen atmosphere, denser than Earth's, methane clouds that build storms, rainfall that carves channels and lakes and seas of liquid methane and ethane. In labs on Earth, Titan-like conditions generate complex organic molecules, tholins, that can act as the raw ingredients for biology. Add to that a likely subsurface ocean of water mixed with ammonia. Low gravity plus dense air even makes flight easy. Physics tilted in our favor. Methane should be destroyed by sunlight over geologic time, so something must be replenishing it. Cryovolcanism, subterranean reservoirs, or chemistry we don't yet grasp. Cassini mapped dune fields made of hydrocarbon sand, but how those grains form and move is still debated. And if a warm interior ocean contacts fresh rock, could hydrothermal energy spark the kind of chemistry that on Earth's seafloor powers entire ecosystems in the dark? NASA's Dragonfly will answer these questions by flying from the equatorial dune fields toward the impact-scarred Selk region, sampling diverse terrains, sniffing organics, and searching for biosignatures in a world with alien seas and orange skies. It's not just a lander, it's a mobile laboratory with wings, built to chase chemistry wherever it leads. Earth taught us that water plus energy plus time can build life. Titan dares us to ask whether a different recipe, other liquids, other temperatures, could do the same. If it can, the definition of habitable changes forever. Other ocean worlds worth watching: Ganymede, bigger than Mercury, wrapped in ice, and the only moon with its own magnetic field. Hubble measurements hint at a deep, salty ocean that may be layered in stacks beneath the crust, like sheets of water and ice sliding over one another. On Earth, salt and moving water drive chemistry. On Ganymede, tides from Jupiter could keep that hidden ocean stirred. ESA's JUICE will probe it up close, asking whether this giant world is more than just rock and frost. Callisto, a fossil on the outside, heavily cratered, ancient, quiet. But models point to a buried ocean insulated by a thick shell. If true, it's a paradox. An old, cold surface hiding a sea that could still carry the ingredients for life. Callisto bathes in less radiation than Europa, making it a calmer laboratory. JUICE flybys will listen for a conductive, salt-rich layer and map the interior, hunting for clues that the deep water is real. Triton, likely a captured world from the Kuiper Belt, orbiting Neptune backward and still alive. Voyager 2 saw nitrogen geysers blasting from its surface, proof that heat is moving inside. Capture and tides could have warmed Triton enough to keep an ocean beneath the crust. If there's energy, water, and organics sealed below, then a far-flung moon at the edge of the solar system might host the chemistry we chase closer to home. Ceres, a dwarf planet between Mars and Jupiter, small but active. NASA's Dawn mission found bright salt deposits in Ocador crater, fingerprints of briny liquids that recently reached the surface. Organics were detected too. On Earth, brines carry chemistry through rock like veins. On Ceres, those veins may still be pulsing under the crust, moving ingredients where they need to go. Before we leave the outer system, look back at Earth, a planet whose miracle is not location but chemistry. Rain gathers, rivers carve, oceans circulate. Sunlight and the planet's heat feed ecosystems from coral reefs to midnight zones. In total darkness at deep-sea vents, microbes eat hydrogen and sulfur and build communities. In Antarctica, life endures in subglacial lakes sealed for millennia. In desert salt flats, Brines concentrate and preserve organics. The rule is simple. Where liquid persists and energy flows, chemistry grows complex and sometimes alive. If Ganymede's layered seas conduct salt-rich currents, if Callisto's deep water touches rock, if Triton's captured heat still drives cycles, if Ceres' brines still move through fractures, then the same rule may play out again. Our probes will listen for it, in fields and spectra, in ratios of carbon and hydrogen, in the fingerprints that living chemistry leaves behind. Many worlds, many oceans. One question that could rewrite our place if it's answered even once. What if life isn't rare at all, but the universe's most patient habit?